Okay, so today we're going to continue with a three-phase full wave or full bridge 6-pass uncontrolled rectifier. Before this, we have three-phase, a half wave or half bridge 3-pass uncontrolled rectifier. But now we're going to extend our analysis. We're going to study the circuits with a three-phase full wave or full bridge 6-pass uncontrolled rectifier. It is called as uncontrolled because we use the diodes. And 6-pass is when we look at the output voltage later on. We're going to explain and we're going to get why this rectifier is known as 6-pass rectifier compared to half wave. It is also known as a 3-pass rectifier. Okay, so to construct the three-phase full wave bridge rectifier, we need another 3 diodes connected to the circuit. So for the half bridge, a full wave, we only have D1, D3, and D5, whereby the cathode, the anode of the diode 1, diode 3, diode 5 is connected to the supply voltage. And now we add another 3 identical diodes on the bottom group. We have D2, D4, D6. Having said that, it is important and it is very, very crucial that we follow the labeling of the arrangement of D1, D3, D5, D2, D4, D6 before we proceed, right? So there is a reason why the diode labeling is always in certain terms of D1, D3, D5, D2, D4, D6. We're going to look at later why this is labeled as the right. So if I can rearrange this circuit to the next circuit here, so I'm going to rearrange so that I'm going to rotate the top group here, D1, D3, D5, 90 degree anti-clockwise or clockwise. We get D1, D3, D5. I'm going to rotate the bottom group here, again 90 degree anti-clockwise. Then I will get D2, D4, D6 in this arrangement. So if you refer to the top group here, this is very much similar to the midpoint converter, the 3-pass or the half wave rectifier. Very much pretty follow similar or exactly the same as a midpoint converter. And the output of this the top group here will be connected to the load R1 and then connect to the end point of the bottom group, and the cathode of the bottom group here will be connected to the supply voltage here. Right, so before we go on the discussing the circuit operations, let's have a look at the points, the nodes that are very important in describing the circuit later on. So we have the neutral point, which is the neutral or the common of the three-phase supply here. And then we have the capital P to denote the output of the top group. And we have N, the capital N here to denote the bottom group, the voltage output, the point of the output bottom groups here. With respect to, we have an N. Small letter here is actually the neutral point here. Right. So for 3-pass rectifier before, we have the rules to identify which diode is on at any particular time. We apply these rules, isn't it? So we have the top group. For the top group here, the diode, which its anode with highest potential will conduct. So it will follow these rules. And for the bottom group here, we'll be following this rule whereby the diode, which its cathode with lowest potential conduct. Right. So once we understand the rules here, then we can simply identify which diodes will be on at any particular time, which diodes is on the top, and which is diode that will be on at bottom group here. So we have a top group and bottom group, P group and N group here. And the output voltage is always parallel to the load, right? Okay, so now let's look at the supply voltage here. So we have V red, V yellow, and V blue of the output. the supply voltage, the three-phase supply voltage, right? So now let's test our understanding. How can we apply these rules at any particular time? So we start at this 0 degree. Okay, let's look at the top group here between D1, D3, D5. The diode, if we look at the rules here, the diode with anode with highest potential will conduct. So if you refer to these 3 voltages at this particular point, we're going to see that the diode, the blue phase voltage is actually at its highest compared to red phase voltage and the yellow phase voltage. So that means during this 0 degree, we have the blue phase voltage will be at its highest potential. Therefore, you're going to see that D5 here will be on. So that's why in that region, you're going to have D5 on, right? At the bottom group here, you're going to see that the yellow phase voltage is actually at its lowest potential. So therefore, D6 yellow, to the diode that connect to the yellow phase on the bottom group, it's actually for the D6, right? D6. Okay, so now as we start to move away from the 0 degree here, right at that 30 degree, whereby we have the intersection between blue phase voltage and red phase voltage, just across that, we're going to now the red voltage is the highest compared to the 3 voltages. Therefore, the diode will be changed or switch from D5 to D1. Okay, so diode 1 will start to turn on from that intersection until we have this diode yellow phase voltage be followed. So at the bottom group here, if you refer to that particular point, we still have D6 to be turned on, to continue to stays on because it is the lowest potential. But when it cross this intersection between the blue and yellow waveform, then we see the blue waveform has its highest or lowest potential, and therefore it changed to D2 here, right? So if you label all the diodes in this waveform, three-phase supply, we're going to have D1, D3, D5, and then the bottom group we have D2, D4, D6, and that's why we have the labeling of the diode is always D1, D3, D5, D2, D4, D6, so that we're going to have a nice arrangement. We're going to look at the diode, a commutation of diode from D1 to D2, D3, D4, D5, D6. So this is how the diodes switch from one diode to another diode. So it is labeled so that in that waveform we have a nice, we have a sequence, a correct sequence of diode operation where I go D1, switch to D2, then D3, D4, D5, D6. Right. So that is why we have the labeling of the diodes, so it's D1, D3, D5, D2. Okay, so now we are interested in looking at the output voltage because that is the ultimate objective, whereby we need to look at this output voltage, the waveform of the output voltage. So to understand that, we go back to the 3-pulse midpoint converter, whereby if you refer to this circuit, so whenever D1 is on, the output voltage VP here will always equals to the supply voltage V red, isn't it? When D3 is on, the P voltage here will equals to the yellow phase voltage, and if D5 is on, it will follow exactly at the yellow phase, blue phase voltages, right? With respect to that N neutral point. So the output of the voltage, if you refer to this point, the P and N, you're going to have the output of that from that P to N will follow the envelopes of the supply voltage, the positive envelopes of the supply voltage. So that will be your VPN. What about on the bottom group? So if D2 is on, then we're going to see that this point, the N point here, will be connected to the neutral point of the supply voltage, and this N will be connected to, if D2 is on, will be connected to blue phase. And then if you have D6 is on, N will be connected to the yellow phase, and if D4 is on, then it will be connected to red phase voltage, right? So therefore, if you look at the waveform, the V and N, the voltage from that point to that point, will follow the envelope of the negative phase voltage, right? So this is your VPN, all right? So that would be VPN here, and this is going to be V and N, the voltage from that point to the V and N, all right? So that's the output voltage. So now let's look at how we can get the output voltage, because that is the ultimate objective, to know or to look at, to observe the output voltage waveform. So to be able for you to understand, to operate, to look at the output voltage, we apply this KVL, right? Because we know that between this point to N is VP, from the positive to neutral point, we have VPN. That will be plus, and this will be minus. And then for the bottom group here, we have plus and N here, V and N. So if you look at the polarity, there will be plus, negative. We have plus, negative, and the output voltage VDC or VD here from that point to that point. So if you apply the rules, the KVL rule from the following that loops, okay, then we have plus VNN minus VPN plus VD, to get the output voltage. So if you rearrange, then the output voltage KVL equals to VPN minus VNN. So if you come back to this output voltage M, so where is the VDC? You just simply subtract the VPN minus VNN, because we have a negative value here. So VPN, so let's say we have this particular point, VPN minus the negative voltage of VNN, then it become VDC. And this is actually the line to line voltages, right? So you will subtract the output voltage, is the result of subtraction between VPN minus VNN. Yeah, so therefore you have this line to line voltage. It will follow the envelope of the line to line voltage. So if I can draw or sketch the output line, the line to line voltage, you can see that the VDC actually follow the envelope of the line to line voltages. So if you count in one cycle, this is one main cycle, we're going to have 1, 2, 3, 4, 5, and then that combined with that will be 6. So there will be 6 bumps or 6 ripple or 6 pulse, and that's why this full bridge rectifier is also known as a 6 pulse rectifier. So which means in one main cycle you have 6 pulse of the output voltage. You have 6 bumps. So if you divide by 360 degrees, so one main cycle is 360 degrees. If you divide by 6, each pulse here will have 60 degree durations. 60 times 6 pulse will be equals to 360 degree. Okay, so what about the input current? So we know that this is your output voltage. right? So this is the output voltage across the R, and if you look at the current of it, it just says simply VDC divided by R. So the output current also equals to the same 6 pulse waveform, but it's scaled down by the factor of R1. So IDC equals to VDC divided by R1. So you will follow the same waveforms here. That will be the output current. So output current is always continuous. The output current is always continuous. So whenever D1 is on, the current ID will follow through ID1. Okay, then it will choose where to go, right? So that's why you have an ID1 here. It's on. If you refer to IR, so IR is a combination of current through ID1 and also the current through ID4, isn't it? It's going through. Okay, so there's ID4 and also we have ID1. This should be ID4, sorry for that. Okay, so this is minus ID4. Okay, so whenever D1 is on, then IR equals to ID1, and whenever D4 is on, it will be equals to minus ID4. So that's why you have a negative current here. Right, so that's all about the voltage of the output voltage of the three-phase full wave bridge rectifier. Now we're going to look at the how to derive for the output voltage, the average of the output voltage, the VDC. How we're going to have this equation to describe the VDC, the average of the output voltage equation. For that, we go back to the notes. Okay, as we take one of the pulse, we know that the duration of the pulse is always pi over 3, which is 60 degrees, right? And as we did to the 3-pulse rectifier, we're going to rearrange, modify the pulse so that the peak of the output voltage is actually centered exactly at a 0 here, and therefore your equations, the equation for the waveforms now change to cos theta. And because this is following the line-to-line voltage, we're going to have V peak line-to-line cos theta to describe the equation, the instantaneous equation of the output voltage. And as for the limit or the angle, we're going to have plus 30 degree, minus 30 degree. Therefore, the pulse duration is 60 degree. So you start with minus pi over 6 and it ends at pi over 6. Okay, so let's look at the integration. So each pulse is 60 degree. So we're going to get the average value of the DC voltage. So you have to divide 1 over pi over 3, the duration of each pulse. And then your integration should be from minus pi over 6 until pi over 6, right? With respect to that limit. You're going to have minus pi over 6 to pi over 6, and the equation now becomes V peak line-to-line cos theta d theta. So I hope you can solve this. I hope you can solve this. Fill in the gaps between the integral and the output equations here. So the voltage, the equation to describe the output voltage is always 3 over pi V peak line to line. So if you are given in terms of phase voltage, you need to change that to, if you're given in terms of RMS, you have to change to the peak value, and it has to be V peak line to line voltage. Okay, right. So now let's move on and focus on the current, the input current, because we know that we need to look at the THD, total harmonic distortions. We're going to also consider the the power factor. So it is best for us to look at the total the input current. Right. So let's consider this circuit. Okay, so let's move on from the purely resistive load to the to the highly inductive R plus L, the inductive load. And in the case we're going to look into the highly inductive load case, whereby the output current is ripple free. So therefore, in this simulation, we're going to replace the R plus L with a constant current IDC. And our target here, our objective here is to look at what will be the output, the input current, the red phase input current. So let's try to simulate. Okay, so let's just focus on the input current. I'm going to remove this, delete the screen, delete the screen again. So this will be the output input current. Let's have a look at the output current as well. Put that together. So the blue waveform there is actually the output current. We know that it is a constant current, you see. So whenever D1 is on, so this is when D1 is on, and this is when D2 is, D4 is on. Then we have this sort of input current, and it carries the output current of IDC and minus IDC, IDC and minus IDC. And so therefore, if you look at the angle, if you refer to the first slides here, so that will be when the voltage VPN, which is 30 degree, and then we have 120 degree, the pulse of the phase supply voltage. So that will be 150 degree, and then you have another 30 degree, 30 degree, so you have 60 degree here, so that will be 210 degree, and then you have further 120 degree, so that point will be 330 degree, and finally you have 360 degree. So now let's look at this current. This is input current, red phase current. Of course, we need to identify what is the THD, total harmonic distortion of this current. And this is known as a quasi-square waveform compared to the square waveform that we had for the full wave rectifier. The single phase full wave rectifier, we have a square waveform, but now for the full wave three-phase rectifier, we have a quasi-square waveform. It seems like a square waveform, but it's not really a square waveform. So we're going to look at the Fourier series of the quasi-square waveform, so that we can obtain the harmonics content, so that we'll be able to calculate what is the RMS of the fundamental component, because the THD requires the fundamental component, the RMS of the fundamental component, and also the RMS of the total current. Okay, so let's look at this note. Okay, so just a recap, the revision on what is a Fourier series. Let's change that to spot. Okay, right. Some revision on the Fourier analysis. So we have this is the series, Fourier series equation. F of t is always a naught over 2. Please refer to the notes before. A naught 2 is always the DC component. And then we have an cos n omega t plus bn sin n omega t. And from that coefficients, that leads to the Cn, sin n omega t plus Vn. So what is the an? You can follow this equation. This is a general equation for an, coefficient an. And this is the general equation for bn. And finally, you have that Cn. So this is just a revision. Have a look on what is the fundamental equation for the Fourier series of Fourier while doing the Fourier analysis. And then this is how you can identify whether the waveform is has any symmetry, even symmetry, odd symmetry, and half-wave symmetry. Okay, so because when the waveform has one of these symmetry or two of symmetry, it will simplify the analysis. Rather than we evaluate for the whole cycles, for the whole 360 degree, if the waveform has any symmetry, it will, you don't have to integrate. You have to evaluate for the whole cycles. Probably you're going to evaluate up to half of the cycles or even to the quarter of the waveforms, right? And this is table 3.1, and with the conditions, if the even symmetry, then you can see the what happens to the coefficient a and bn, right? So everything's in the notes here, so I can zoom here. So if you are even, then you can see that bn is always 0. What exists is only an. But if the waveform is odd symmetry, all the coefficient an coefficient will be equals to 0, but bn equals to that. So, and if you have an odd, we refer to that odd and quarter wave, an is 0 for all h. Right? So no coefficient an is equals to 0 for all h, but bn only exists for odd harmonics, and you only integrate up to pi over 2, which is 90 degree, quarter of the wave. But bn is 0 for even harmonics, right? So this is just a revision, recap on how the Fourier analysis. Okay, let's move to the quasi-square waveform. Right, so if you refer to your the input current, it is a quasi-square waveform, and we have this degree, 30 degree, then you have the pulse is 130 degree, so therefore you have the next angle here is 150 degree, there is a 60 degree apart, therefore that will be 210, and further 120 degree durations, and then we have 330 degree, right? So before we proceed, we need to look at the symmetry of the waveform. So if you refer to this quasi-square waveform, it is by observation, I already write it, but it is a observation. The current waveform is odd and half wave symmetry. Therefore, the waveform is also odd and quarter wave symmetry. So if you refer back to the table 3.1 just now, an is always 0 for all n harmonics, and therefore that's including the DC average mean component, which is a naught over 2. That also equals to 0. bn is 0 for even harmonics, so there will be no coefficient, no Cn at 0, at 2, 6, 8, 10. All the even harmonics will be 0. bn is only exists for odd harmonics, which is 1, 3, 5, 7. And the possibility of n for this quasi-square waveform is at 1, 3, 5, 7, all the odd harmonics. Now we're going to evaluate and look at the Fourier analysis to get the equation to describe the Fourier series equation to describe quasi-square waveform. So we start with hence bn will be evaluated for n odd and up to quarter of the wave, right? So therefore, since bn, this is a general equation, Bn is 2 over t 0 to t f of t sine n omega t dt. Now your Bn becomes 2 over t over 4 because we only evaluate up to quarter of the wave because it is quarter and odd and quarter wave. So you have 2 divided by 2 over 4 and you integrate from 0 to t over 4. Right? F of t sine n omega t dt, and then it is convenient to convert to radian, therefore t is changed to 2 pi, that's why you have 2 over 2 pi over 4, and then your upper limit here becomes 2 pi over 4, and then therefore finally you have Bn equals to 4 over pi, and you have the integration from 0 to pi over 2 f theta sine n theta. For the quasi-square waveform of the input current IAC, so Bn becomes 4 over pi, this is a general equation again, 0 to pi over 2 IAC theta sine n theta d theta. And now we look at the equations, look at the waveform. This is your waveform. You only actually integrate from 30 degree to pi over 2 because it's a square wave, quasi-square waveform. We only evaluate up to pi over 2. So we start from 30 degree, which is pi over 6, and it ends at pi over 2, which is 90 degrees here. Right? So for that, it become Bn 4 IDC over n pi cos n pi over 6. So you replace that pi over 2 inside your here. And you have cos n pi over 6 minus cos n pi over 2. So since n exists only for odd values, 1, 3, 5, 7, 9, because of the odd and quarter wave condition, and if we substitute n with triplet numbers, 3, 9, 15, 21, and so on, we're going to see that the first component here, which is cos n pi over 6, will go to 0 for n triplet. And for the second component here, which is cos n pi over 2, will be 0 for all n odd harmonics. Okay? These terms is always goes to 0, but for the first term here, it is only 0 for triplet harmonics 3, 9, 15, 21. Therefore, if you list the number of harmonics, the Bn only exists for IDC over n pi cos n pi over 6, and you have to cancel out all the triplet harmonics, which is 3, 9, 15. The next will be what? 15, 21, and the rest. Okay, so it is Bn only exists for odd but no triplet harmonics. Right? So therefore, your Cn, because our target is to get Cn, is the amplitude, the magnitude of An squared plus Bn squared. Therefore, we put in the amplitude, right, absolute value, which is 4 IDC over n pi cos n pi is 6, because we have to be careful for certain value of n, for example 5, 7, 17, Cn is it will become negative value, but we know that Cn is always positive because of that modular, okay, of this absolute value. So therefore you have for the angle, it's always An over Bn, so An is 0 since An is 0, right? So the angle is 0. If you write the Fourier series, so you have a summation of n from 1 to infinity, 4 IDC over n pi cos n pi over 6 sine n omega t, but there is no triplet. It is odd but no triplet harmonic. So if you list down, it becomes 1, 5, 7, 11, 13, 17. And finally, your Fourier series equations is 4 IDC over pi cos pi over 6 sine omega t, and then the next amplitude will be 4 IDC for 5 pi cos 5 pi over 6 sine omega 5 omega t. Next will be 4 IDC over 7 pi cos 7 pi over 6 sine 7 omega t, and the rest, right? So this is the Fourier series of the quasi-square waveform. And if you want to look at the spectrum of that, you will see this spectrum, harmonic spectrum of a quasi-square waveform. There will be a components that are fundamentals, the 5th, 7th, 11, and there is no triplet harmonics. So if you refer to this, there's no triplet harmonics here because it is 0. Right? So now you can compare between the characteristic of the quasi-square waveform as well as the square waveform. What is different between the two? And you can try what will be the THD and power factor of the quasi-square waveform. Right? I think that's it for the square waveform. I'm going to continue with the rectifier with the LS in the front end.